Look up inside the Pantheon in Rome, and you're staring at the largest unreinforced concrete dome ever built. It was dedicated nearly 2,000 years ago, yet this structure, along with Roman seawalls constantly hammered by the ocean, remains pristine. Compare that to modern concrete. We embed steel rebar inside it for strength, but that steel inevitably rusts. As it oxidizes, the metal expands and cracks the structure from the inside out. This design flaw creates a massive maintenance debt. In the United States alone, the cost to repair and rebuild crumbling concrete infrastructure is projected to reach into the trillions of dollars. We built 20th century civilization on a material with a built-in expiration date. Meanwhile, ancient Roman walls continue to outlive modern ones by thousands of years. If you look closely at a sample of Roman concrete, you'll find small, bright white mineral chunks embedded in the mix. These white chunks are known as lime clasts. For a long time, engineers dismissed these chunks as evidence of low-quality work. The prevailing theory was that the ancient Roman builders were simply sloppy mixers who didn't properly blend their ingredients. But researchers at MIT questioned that assumption. Why would an empire that spent centuries optimizing its construction recipes be so careless during the final mix? Our belief that modern engineering is inherently superior left us with a massive blind spot. We ignored a deliberate technical choice for decades because we assumed it was a mistake. This chemical mapping of ancient Roman concrete reveals the secret. Look at these clusters of calcium in red. While historical texts suggested the Romans used a pre-mixed lime paste, this data shows they were using something much more reactive. The Raman spectrograph proves that these samples were formed at extreme temperatures. This is a result of hot mixing, adding dry reactive quicklime directly into the volcanic ash and water. When water hits that dry quicklime, it triggers a violent reaction that releases massive amounts of heat. The concrete reaches temperatures up to 200 degrees Celsius during the mix. This intense environment prevents the lime from fully dissolving, leaving it trapped in the concrete as brittle, high-surface area reservoirs. These white chunks act as stored chemical caches, sitting dormant inside the structure until they are needed to perform a specific function. That function is triggered when a fracture forms. As rainwater seeps into the crack, it travels through the matrix until it reaches a lime blast. The water dissolves the calcium inside that chunk, creating a highly alkaline mineral-rich solution that fills the open space. This solution then solidifies into calcite, a mineral that physically plugs the fracture and seals the wall against further water damage. This reaction happens automatically in a matter of weeks, stopping structural failure before the crack can expand. Modern concrete is destroyed by water. Roman concrete uses water as a key ingredient in its own repair. If this material was so durable, it raises a question: how was the recipe lost? For over 1,000 years, the technology was linked to imperial funding. Only a massive centralized economy could bankroll the logistics required to transport these reactive materials for public works. When the Roman state collapsed, that funding evaporated. Without emperors to pay for these experimental high-cost mixtures, builders reverted to simpler, cheaper mortars. The hot mixed concrete revolution ended because the specific economic pressures that demanded such complex materials no longer existed. We can see the results in the lab. Researchers created hot mixed samples, cracked them, and ran water through the gap. Look at this blue line representing the hot mix sample. Within 15 days, the water flow dropped to zero, proving the concrete completely sealed itself. Engineers are now commercializing this ancient method. By using it to build infrastructure that fixes itself, we can massively reduce the carbon emissions tied to constant reconstruction. By re-evaluating what we dismissed as ancient errors, we found a way to build a world designed to last rather than designed to fail.